All right, welcome back. This is lecture 2 of a lecture series on the theory of quantum entanglement for the SheQuantum platform, which is supporting women doing research and learning in quantum information science. Last time, I gave some kind of rough introduction to the lecture series, told you that it was going to be about entanglement theory and some of its applications. And then we went into a bit of the math behind density matrices that describes the state of a quantum system. And we talked about single quantum systems last time, and now we're going to talk about multiple quantum systems. Why do we want to talk about multiple quantum systems? Well, quantum computers and quantum information processing devices more generally are not particularly useful if they consist of just a single qubit, right? It only becomes useful if you have many, many qubits. As an example, here's a nice picture. I think I must have stolen this from Twitter or something like that, of IBM's Hummingbird chip. That's a 65 qubit universal quantum computer. If you're not aware of it, I think many people are aware of it. You can create an account with IBM and program their quantum computer. I don't think the 65 qubit one is available publicly, but I think at least 20 qubit ones are available for programming. So you could have some fun with that. Okay, so now let's move on and talk about the math behind composite quantum systems. All right, so now let's think about two parties. One we'll call Alice and another we'll call Bob. Okay, so last time we talked about density matrices for individual quantum systems. So Alice's system can be described by a density matrix rho, and Bob's system can be described by a density matrix sigma. Okay, now let's suppose that they've never interacted in the past, and then they sort of, come close to each other. Then the state of their joint system we describe by the tensor product. Okay, so I don't know if most people learn this operation in a standard linear algebra course, but it's very important for quantum computing and quantum information science. Okay, so the joint system will be described by the tensor product of Alice's density matrix rho and Bob's density matrix sigma. Okay. And then what we do is we use the system labels to say who has what. So we use A to say, okay, that part belongs to Alice and that part belongs to Bob. In this lecture series, I don't think I have the mathematical description of the tensor product. That's something you can certainly pause the video now and Google tensor product. It also goes by the name Kronecker product. And I'm sure there's an extensive Wikipedia on that. It's also in the book that I mentioned that I wrote with Sumit Khatri. Our book is called Principles of Quantum Communication Theory and Modern Approach. And we go through that in the chapter on quantum mechanics. Okay, so it might be worthwhile, if you haven't seen this before, to take a pause and check it out. Okay, so a generic state of a bipartite system, it acts on what we call a tensor product Hilbert space. For the purpose of this lecture, you can just think of this as a complex vector space, a finite dimensional complex vector space. So a generic state, it acts on a tensor product vector space. So how do you think about this? Suppose we have an orthonormal basis for Alice's Hilbert space, her vector space. And suppose we have a possibly different orthonormal basis for Bob's. Then if you take the tensor product of the individual vectors and you get a whole list of them, right? So the number that you'll have will be the product of the number in this set and the number in this set. So this set that you get by taking the tensor product of the vectors, that will be an orthonormal basis for the tensor product Hilbert space. So that's an important concept. And then what you can do is you can use this basis to write down a generic state, a generic bipartite state of the tensor product Hilbert space. So rather than just 2 indices like we had before, now we're going to have 4, okay? And these you could arrange in a matrix, okay? But then you would have, you would be labeling the columns, sorry, the rows of the matrix with 2 indices, I and J, and you'd be labeling the columns of the matrix with the 2 indices, K and L, okay? So now let's get to define what is quantum entanglement. This is some picture of entangled particles or some artistic description of what entanglement might look like. Okay, so to motivate and define what entanglement is, let's first define what it is not. Okay, so let's suppose that Alice prepares the state rho x and Bob prepares the state sigma x. And let's suppose that they prepare these states based on the outcome of a probability distribution, right? So like maybe you flip a coin, if you get heads, they would prepare rho 0, sigma 0. If you get, if the outcome of the coin flip is tails, they prepare rho 1 and sigma 1. So that's an example. But the random variable could have more letters in it other than just 2 letters. Okay. So if they do this, then the state of their joint system is a convex combination, or this probabilistic mixture of the individual states. Okay. So such a state is called a separable state, or it's also known as an unentangled state, or it is not entangled, okay? And why do we say that? Well, they didn't need any sort of quantum interaction to prepare this state. How is it prepared? Someone else could flip the coin and then communicate the outcome of the coin over a classical channel, over an ordinary channel to both Alice and Bob, right? So if the coin flip outcome is heads, then a third party could communicate, oh, the coin flip was heads to both Alice and Bob. And then they would prepare the state based on the outcome of the coin flip. And if it were tails, this other person could tell them that. So the point is, this state can be prepared by means of what's called local operations and classical communication. This gets abbreviated as LOCC. If you go out and look at the research literature, you'll always see this term LOCC. And that's really what it is. There's the classical communication to communicate the X, and then Alice uses a local operation to prepare her quantum system in the state rho X, and Bob uses a local operation to prepare sigma X. Okay. And then one thing you can prove, and maybe you'd want to try this as an exercise, you can use the spectral decomposition of rho X and a spectral decomposition of sigma X, and then you could collect the variable X and then the index from this spectral decomposition and the index from this one into like a super index or super variable. And it follows that every separable state you can actually write as a convex combination of pure product states. Okay, so that ends up being important for some applications, but it's just a basic fact that it's always possible to do so. In the book with Schmidt, we do show how that is possible in the section on entanglement. Okay, and so this is what a separable state, and a state is entangled if it cannot be written in this form. Okay, so from that perspective, maybe the definition is a little complicated, but that is the definition. Okay, so to prepare an entangled state, you need some sort of quantum interaction to do so. An example would be a controlled NOT gate. If you've studied quantum computing before, you'll see the controlled NOT gates. And that can be used to establish entanglement. Okay, so yes, let's talk about an example of an entangled state. And this perhaps is the most important, or a state that appears quite frequently. And it goes by different names. It goes by Bell state. It goes by EPR pair after Einstein, Podolsky, and Rosen. In quantum information language, it's called E-bit, okay, because it's like entangled bit. It's like one bit of entanglement. And what is the state? It is a uniform superposition of two possibilities, 0 for Alice and 0 for Bob, or 1 for Alice and 1 for Bob, okay? And so this perfect entangled state is useful for teleportation. It's useful for superintense coding. It's useful for making a secret key. We might get into that a bit later, why it's useful for that. If you write it down in matrix form, it looks like this. So you'd have to write down the vector form for 0, 0 plus 1, 1. What would that look like? I didn't write it on the slide, but it'd be a vector with 4 rows in a single column. And the top entry would be 1 over root 2. The bottom entry would be 1 over root 2. And the other 2 would be 0. So if you take the outer product of that vector with itself, you get this 4 by 4 matrix. Okay, that's what it looks like. And there are just 1s in the 4 corners of the matrix and the 1/2 to make sure that it's normalized, right? So you can check that this matrix is positive semi-definite. That might be an interesting exercise. You know, open up MATLAB or Python or Octave, one of those, and you can plug in this matrix and check if it's positive semi-definite. How do you do that? Do the eigen decomposition. And when you do it, you should find that there's one eigenvalue with the one eigenvector with eigenvalue 1, and the others will have eigenvalue 0. So it's a rank 1 matrix, and it's a pure state. Okay, just to connect to concepts we talked about previously. How do you see that this is entangled? This is a more difficult exercise. What you can do is you can consider all possible product states of Alice and Bob, all possible pure product states. So psi tensor phi. And you can show that the overlap of this vector, this E-bit, with all possible product vectors is never larger than 1/2. Okay. So that means that it's impossible to write phi as this tensor product. For if it were, then there would be some choice of psi and phi such that the inner product would be 1. But it's not true. It's always less than 1/2. That's something you can prove. It's a more challenging exercise. What you need to use is the Cauchy-Schwarz inequality, which is a famous inequality used all the time in all of mathematics. Okay. So that's a rough proof that this state is entangled. It cannot be written as a pure product state. And then furthermore, if you were to take convex combinations of density matrices corresponding to this vector, then the overlap would not exceed 1/2 either. Okay. So yes, so it's impossible to write this as a separable state. Okay, so I want to talk about this tool, and then that'll be the final concept of this lecture. And it's something called the Schmidt decomposition theorem. This is an extremely important tool in quantum information science. We use it all the time. You'll use it in quantum computing. You'll use it in quantum communication, etc. It's all over the place. So the theorem says that if you have any two-party unit vector, so that's a vector in this tensor product Hilbert space with norm equal to 1, you can write it in this form, okay? And so what is this form? Well, you have these coordinated values here, like you have I for Alice, I for Bob. And so if they were to do measurements in this basis, then their outcomes would always agree. These are square roots of probabilities, as you'd expect. And so it's always possible to do this. Okay. The vector of the square roots of these probabilities, these are called the Schmidt coefficients. And the Schmidt rank of this psi is equal to the number of Schmidt coefficients, okay? And the Schmidt rank is always going to be less than or equal to the minimum of Alice and Bob, the dimension of their Hilbert spaces, okay? So I'm not going to show you how to prove this. That's another thing you can look up in the book. And the proof is based on the singular value decomposition, which is like the pinnacle theorem in a course on linear algebra. Okay, so let's stop there and let's pick up for the next time.